In this video we're going to be looking at how we can simplify the Boolean algebra expressions that we were generating in the previous video. So in this case, Boolean simplifications are all based on a whole series of rules which you're just going to have to remember. But they can do pretty cool things like take this expression and they can prove that that is the same as this. So in fact the whole C part is not required, the gate required for these is not required, right? So you can do a simplification like that using Boolean algebra. And that's good because that's less hardware, which means less power consumed, which means a smaller, more efficient device. That then means hopefully that's going to save you and your customers money in the products you are implementing. So the few rules for you guys to remember. Simplification rules, I call them, or sort of laws of Boolean algebra. So we're only going to cover the ones with ands and ors. There are ones with XOR, but we're not going to cover them as part of this video series. So operations with logic 0. A and 0 equals 0, always. It doesn't matter what A is, if the other input is 0, then the output has to be 0 as well. A or 0 is always equal to A. Right? If A is 1, then it's going to be 1 here. If A is 0, it's going to be 0 here. So you can see how it moves itself across. Rules with logic 1. A and 1 is always equal to A. Alright, if A is equal to 0, output is 0, A is 1, A, 1 and 1, we get 1 on the output. Versus or 1 will always give us a 1. Doesn't matter what A is doing, the fact that one of our inputs is 1 means that we're guaranteed to have our output to be equal to 1. Okay, complements. In fact, let's do the same variable. That's probably an easier one. So the same variable, A and A is the same as just the single variable, and correspondingly A or A is also equal to the same input variable. Right, so those are just the rules associated with the same variable. Complement of a variable. So these are ones like A and not A is always equal to 0, whereas A or not A is always equal to 1. One of these has to be equal to 1. If this one's 0, that one's 1. If this one's 1, 0, that one's 1, and so forth. And then finally, our double inversion rule. It states that not A is the same as just A. You've got rid of effectively the inversion. Okay, invert it once, 0 goes to 1, invert it again, 1 goes to 0, you're back where you started. All of these rules you should be able to prove to yourself. Right? If they're not directly obvious, try reasoning them out by drawing truth tables. Right? They should all intuitively make sense to you going forward. The final one that we're going to look at is what's known as the De Morgan's theorem. And this one states that a NAND gate is equivalent to an OR gate with inverting inputs, and a NOR gate is equivalent to an AND gate with inverting inputs. So let's have a quick look at how this one actually works. So De Morgan's rules allow you to take NANDs or NOR gates and convert them to forms that may be easier to help you simplify your circuit. And the easiest way to do this is if we had the top example there, an AND gate with inverting output. Okay, so we have not AB, that is equivalent to an OR gate with inverting inputs. And the way I remember how to do this is step 1, invert all inputs. Step 2, invert the symbol. I mean that in a very loose sense. And then 3, invert the output. So let's see how this works. A and B invert both inputs, both get bubbles on them. Invert the symbol, AND goes to OR would go to AND. And then the final step, invert the output. Bubble goes to no bubble. So let's see how it works for the NOR gate example. AB, so this is the same as in Boolean Algebra, A or B, the invert of A or B. Alright, so first thing is invert the inputs, then invert the symbol, OR goes to AND, and then invert the output. Bubble goes to no bubble. And so you see now we have an AND gate with inverting inputs. A, B. If the bar, and note this, if the bar is continuous, then it's on the output. If it's not continuous, as we've done here, then it's purely on the inputs themselves. Quite important you see the difference between those two. This is a NOR gate, this is not a NOR gate. So, these are your rules. Let's put them into practice and see how we can solve this problem up here and one more. Okay, first problem. Q equals A and not B, or A and not B and C. Okay, one of the things that we can do when working with Boolean algebra expressions is we can expand, factor, reorder as per normal scalar mathematics. Okay, and by that I mean we can do things like A and B is the same as B and A. Okay, A, B or C is the same as AB plus AC, and so forth. So the same rules that we're used to in mathematics also apply in Boolean algebra. The only ones we've got to be watching out for are things like 1 or 1. Okay, obviously in mathematics that would equal 2. In this case 1 or 1 equals 1. So sort of watching out for little peculiarities, but most of them are pretty straightforward, as we'll see. So looking at this one, let's factor this one using A and B. A and not B, sorry. So A and not B. Now we haven't got anything here, so we can assume 1 or C. And the reason we can do that is looking at our rules. A and 1 is still the same as just A. Alright, so putting the 1 in there has made no difference to that particular circuit. Alright, in this case we can see that the next step we've got 1 or C. So 1 or A, or 1 or C in this case, is the same as just 1. So we have effectively A or B and then 1 in brackets, and A and B, or A and 1 equals A, takes us to this expression here. So we would go 1 plus C equals 1 to get to here, and then we'd have that expression there, and this one is simply a factor. right? And always a good idea to write down, especially if I'm marking it, what your steps were all the way through. Don't just stop here and then expect me to work out what the final form is, or don't just jump from the top one to the bottom one. I want to see the working as you go through these problems. Right, let's have another one that's slightly more complicated. Q equals A, B, not A plus B, not B plus B. Now when I look at this one, a couple of things I will realize immediately. This bracket here looks interesting, not B or B. Right, we've already seen that complement of a variable, A or not A is equal to 1. So we know straight away, applying that rule, it's going to be equal to 1. And we've got a NAND gate here. So we can use De Morgan's rule to be able to modify that from NAND into this OR gate with inverting inputs. And that makes it a little bit easier to work with because we've only got single variables then. So applying just the AND rule, we end up with this expression. Anything ANDed with 1 is the same as its original expression, so let's just cancel that out. Alright, but I've still included it and I've drawn a line through it to show you that I've done that. We're then going to apply De Morgan's on this part here so that we get not A or not B and not A or B. At this point we can expand the brackets out, okay, just like normal mathematics. Not A, or not A, B, or not A, not B, or not B and B. Okay, a few interesting ones. This one, alright, as we've seen as per our rules, A and not A is equal to 0. Okay, so that becomes 0. We've got a common factor here that we can use to factorize this expression. A, not A, or not B or B, plus 0. Okay, in this case, B or not B, we know is equal to 1, has to be. So we get, just going down and writing this explicitly, plus 1 plus 0. Going forward, we know that not A plus 1, anything plus 1 or anything ordered with 1 has to be equal to itself. So we get equal to 1. So we get not A, 1 in brackets plus 0. And then finally we get not A plus 0. Well, we know that, once again, same thing again, not A plus 1, not plus, and 1 is equal to not A in this case, and then not A or 0 is equal to not A. So the solution then is not A. Right, just checking those rules. A and 0, A or 0 equals A, so that's this one here. A and 1 equals A, this one here. A or 1 equals 1. Alright, not A or A equals 1, as we've done here as well. So that all makes sense. So it's a number of steps, easy to make mistakes. You're always looking for the minimal form. Okay, you're not just looking for, are we going to do one simplification? It was optional to apply De Morgan's in this case. We could have arrived at the same answer a different way. But I like to get rid of these terms which have two variables and expand everything out into single variables if possible. So you're always looking for simplifications that De Morgans can make. And normally you're looking for either NAND gates or NOR gates. Those are the ones. But remember, you can go back again. These rules apply in both directions. So if you see them in the other way, then by all means use them the other way as well. So, quick summary, Boolean simplification. Remember your simplification rules, make sure you understand them and can apply them. Practice De Morgans. Okay, my little 3-step process here works quite well. Standard mathematical rules apply, and do examples. All right, this will help you learn and apply these rules faster and without error.